So I think there's this very specific, uh, very seductive fantasy that a lot of us have probably entertained,
Oh, yeah.
especially late at night when you're just doom scrolling. You see a video of a wildfire in California or maybe a glacier collapsing in the Arctic, and your brain just sort of looks at the exit door.
Right. You want an escape hatch.
Exactly. You start thinking about that classic sci-fi dream,
Yeah.
the whole Elon Musk vision of the future.
The Mars option.
Yes, the Mars option. The idea that if we really mess things up here on Earth, if the weather goes completely haywire or the grid fails,
Mm-hmm.
we have a backup plan.
Look, we can just pack up a spaceship and blast off.
Right, and we'll just terraform the red planet and start fresh.
Yeah.
It feels like the ultimate reset button for civilization.
It is a really compelling narrative. It speaks to that whole frontier spirit, that idea that human beings can always just move west or, in this case, move up. But if we're going to be honest with the source material we have in front of us today, specifically we're looking at the Climate Evolution and Energy Resources Management text and the lecture notes on ECIA, we really have to shatter that illusion right out of the gate.
Shatter. I mean, that feels a little harsh for a deep dive.
It might be harsh, but it's totally necessary. The texts are incredibly clear on the thermodynamics of this whole Mars idea.
Okay, let's get into that.
The energy required to actually terraform an inhospitable planet like Mars, to take a dead, frozen, irradiated rock and convert it into a biosphere that supports human biology, it is currently completely outside our scope.
So it's just physically not feasible.
And for the foreseeable future, too, we cannot simply engineer a brand new atmosphere on a dead planet when we are actively struggling to maintain the perfectly calibrated atmosphere we already have on this one.
So the whole Plan B thing is effectively a bust.
It is a dangerous illusion, honestly. And I'm not just being a pessimist here. The source material quotes the former UN Secretary General Ban Ki-moon on this, and he put it about as bluntly as you possibly can.
Oh, I have that quote right here in our notes. He said, quote, "There is no Plan B because we don't have a planet B."
It's a slogan we hear a lot, but when you actually sit with the physics of it, it really changes the room.
Yeah.
It basically means the door is locked, we are inside the house, the smoke alarm is going off, and there is no fire escape. We have to fix the room we are currently standing in.
And that really sets the stage for the mission of this deep dive today. For everyone listening, we are going to strip away the politics, the shouting matches the punditry, and we're going to look at the actual machinery of the planet.
Right. We want to understand the gears and the levers.
Exactly. And to do that, we have to look at the clock.
You're referring to the visual in the presentation slides, right? The one with the clock face.
Yeah, that's dark image of the clock.
It shows the hands ticking right toward the 11th hour. It feels ominous because it's meant to be ominous.
For sure.
For you listening to this right now, climate change might just mean your insurance premiums go up, or maybe you have to run your air conditioning a bit longer into September.
An inconvenience, mostly.
Right. But the text describes a visit by the current UN Secretary General Antonio Guterres to the Tuvalu Islands.
Tuvalu, that's the small nation in the Pacific, right?
Yeah, a low-lying Pacific island nation. And for them, the clock isn't about inconvenience at all. It's about erasure.
Total geographical erasure.
Exactly. If the sea level projections in these reports hold true, Tuvalu doesn't just have a bad storm season, it literally ceases to be a landmass.
That is just a staggering thought. I mean, if the physical land disappears, is it still a country?
And that is the huge existential question. Do they keep their seat at the UN? Do they still issue passports?
Where do the people even go?
Right. It creates this unprecedented legal and moral crisis that our current international framework is just not built to handle. So when we talk about urgency today, that is the baseline we are working from.
Okay, so the stakes are absolute. Now I want to tease something for you listening right now.
Yeah.
Later in this deep dive, we are going to reveal who the real villain of this story is. Because I think most of us just assume it's cars or airplanes.
And most people would be entirely wrong about that.
The data shows a massive giant hiding in plain sight, and it's probably not what you think.
But before we get to that twist, we really need to understand the rules of the game here. The source material takes us back to the late 1980s to define the actual limits of our world.
1987 to be precise. That's the publication of the Brundtland Report.
Titled Our Common Future.
Right. This was the report commissioned by the UN and led by Gro Harlem Brundtland, the former Prime Minister of Norway.
Correct. And this document is super pivotal because it gave us the formal definition of sustainable development.
Which is helpful because sustainability is such a buzzword now.
Oh, absolutely. It gets slapped on everything from shampoo bottles to sneaker boxes these days. It's really lost a lot of its punch.
It feels like marketing fluff half the time, to be honest.
Mhm.
But what was the original rigorous definition from the report?
It's actually a very specific contract. The report defined sustainable development as progress that meets the needs of the present without compromising the ability of future generations to meet their own needs.
Without compromising the ability of future generations, it sounds almost like an intergenerational loan.
Precisely.
Yeah.
We can eat from the garden today, provided we don't salt the earth for the people who need to eat tomorrow.
But if you look at the data in these PDFs, specifically regarding Earth Overshoot Day, it becomes painfully clear that we have defaulted on that loan.
Big time.
Let's unpack Earth Overshoot Day for a second, because I'm looking at the charts here, and it's essentially a calendar date, right?
Think of it like a salary. Imagine the Earth pays us a salary of renewable resources every single year,
Okay, a budget.
right? A certain amount of fresh water, a certain amount of timber regrowth, a certain capacity to absorb carbon dioxide. That's our budget for the year.
Got it.
Earth Overshoot Day is the specific date on the calendar when we have spent that entire salary. Every single day after that date, we are putting our lifestyle on the credit card.
We're dipping into the capital.
Exactly. We're cutting down trees faster than they can grow back. We're pumping aquifers faster than the rain can refill them.
So in a truly sustainable world, Earth Overshoot Day would land on December 31st. We'd just break even.
Exactly. But we are nowhere near December 31st. And what is really fascinating and frankly pretty disturbing in the source material is the huge inequality of this consumption when you break it down country by country.
I was looking at those exact charts. The disparity is wild. Let's look at the hyper-consumers first. The text highlights Qatar.
Qatar is definitely the extreme example here. Their overshoot day lands in mid-February.
Mid-February. That's insane.
Yeah, by Valentine's Day, Qatar has used up its entire ecological allowance for the whole year, for the remaining 10.5 months that society is running purely on ecological debt.
That is nearly incomprehensible. But, okay, Qatar is a very specific case, right? It's a desert. They have immense oil wealth, and they have massively high energy needs for things like water desalination.
True.
What about somewhere more standard?
Let's look at the middle ground in the data then. The text cites Portugal and Poland. Their overshoot day hits in mid-spring, usually around May.
So even in Europe, where you have robust recycling programs and extensive public transit, by the time you're planting your summer garden, you've already eaten the entire year's lunch.
Correct. The analysis notes that for a society like Portugal to sustain its current level of consumption, you would need the equivalent of nearly 3.5 Portugals.
But of course, there is only one Portugal.
Exactly. And then there's a visual in there that I found really haunting. It's a map of Japan. And it asks a very simple question. How many Japans does Japan need?
And the answer is 6.6.
6.6 Japans. To keep the lights on in Tokyo, to keep the industries running, and the sushi flowing at the current Japanese standard of living, you would need the ecological biocapacity of almost 7 Japanese archipelagos.
And since they don't have that extra land, they have to import that biocapacity from elsewhere.
They are effectively outsourcing their depletion to other parts of the world.
It really drives home the fact that we are aggressively borrowing resources from a future that just cannot pay us back. But here's the thing. We are spending resources we don't have, but the bill doesn't come in the mail.
No, it does not.
It comes in the form of heat.
Exactly. The ultimate debt collection agency here is the laws of thermodynamics.
Now, I have to play devil's advocate for just a moment here, because we all have that uncle at Thanksgiving dinner. You know the one. He holds up a turkey leg and points out the window and says, "Look, it's cold outside." And besides, the climate has always changed. There were ice ages way before there were SUVs. This is just natural.
And you know what? You should probably tell that uncle that he is technically right.
Wait, really? I feel like that's the wrong answer to give him.
Well, he is right about the history, but he is completely wrong about the rate of change. The source material is very careful to distinguish between natural climate variability and anthropogenic forcing.
Anthropogenic meaning human-caused.
Right. So let's look at the natural part first, to be fair to your uncle. The text mentions Milankovitch cycles.
Milankovitch cycles. That sounds like a plot device in a Cold War spy novel.
It does, but it's actually astrophysics. It refers to the Earth's orbit around the sun. We tend to think of our orbit as a perfect circle, but it's not. It's an ellipse.
Okay, an oval shape.
Yes, and that shape stretches and squashes over long periods of roughly 100,000 years.
So because it's an oval, Sometimes we are physically closer to the fire, so to speak.
Yes, and in fact, there is this counterintuitive fact in the notes that always surprises people. In the northern hemisphere, the Earth is actually closest to the sun at a point called perihelion during our winter.
Wait, we are closest to the sun when it's coldest outside for us.
In the north, yes, which perfectly proves that distance isn't the only factor at play. It's the tilt of the Earth's axis that actually gives us our seasons.
Right.
But these Milankovitch cycles, the wobble of the axis, the tilt, the orbital shape, they drive major climatic events like the ice ages. But here is the crucial distinction we have to make.
Which is?
These natural cycles happen over tens of thousands of years. They are incredibly slow. Nature has time to migrate. It has time to adapt and evolve to these changes.
And what we are currently doing is decidedly not slow.
Not at all. We are stepping on the gas. We are shifting the global climate far faster than the planet's biological capacity to adjust to it. And the mechanic for this, the main engine of this incredible acceleration, is the greenhouse effect.
Let's break that down,
Okay.
because I think we all learned the whole blanket analogy in grade school, but the text gets a bit more specific about the actual atmospheric physics.
A blanket is a fine starting point, but let's look at the mirror effect instead. Think about solar energy coming in from the sun as shortwave radiation. That's UV light, visible light. It's punchy. Yeah, it punches right through the atmosphere and hits the ground.
Okay, so the light gets in easily.
The Earth absorbs that shortwave radiation and warms up. Then the planet tries to cool itself down by radiating that energy back out into space. But it radiates it back as long-wave thermal radiation, basically just heat.
So light comes in easily, but heat tries to leave.
Exactly. And the greenhouse gases in our atmosphere act like a one-way mirror. They let the shortwave light in just fine, but they trap the long-wave heat trying to escape. And the text highlights a surprising fact. Water vapor is actually the most abundant greenhouse gas.
Water vapor. But we aren't regulating clouds or steam.
No, we aren't. But water vapor acts as a massive amplifier. As the planet gets warmer because of the other gases we pump out, you get more evaporation from the oceans.
Right, warmer air holds more moisture.
And more moisture in the air traps even more heat. It creates this suffocating feedback loop that just drives temperatures higher and higher.
But the trigger for that whole loop, the thing starting the warring, are the trace gases, the chemical culprits.
This is where the atmospheric chemistry gets fascinating. If you take a deep breath right now, 99% of what you just inhaled is nitrogen and oxygen. And those gases are totally neutral. They do not trap heat.
So the entire climate crisis is being driven by the remaining 1%.
Less than 1%, actually. The fate of human civilization rests on these tiny trace fractions of gas.
That's wild. Let's look at the list in the report. Obviously, you have carbon dioxide, CO2.
The main industrial byproduct.
Right. Driven by burning fossil fuels and making cement and all that. The levels have surged to 423.9 parts per million as of early 2024.
Which is a massive, massive spike from any historical baseline. But then you also have methane, CH4.
The cow connection.
The agricultural connection, yes. The text specifically mentions enteric fermentation.
Which is a very polite scientific way of saying cow burps.
Essentially, yes.
Yeah.
But you have to consider the sheer scale of it. A single 700-kilogram cow, and that is a massive animal, produces huge amounts of methane through its digestion and respiration.
And methane levels are over 1,940 parts per billion now.
And methane is a much more potent heat trapper than CO2. Even if it doesn't stay in the atmosphere nearly as long, it traps way more heat while it's there.
We also have nitrous oxide, N2O.
Right, coming largely from diesel engines and agricultural fertilizers.
But the group of gases that really scared me in the reading was the F gases.
The fluorinated gases. Yes, these are the hidden villains of the story. We use them mostly for refrigeration and air conditioning systems.
Which is deeply ironic if you think about it. We use them to cool the inside of our homes, and they heat the outside planet.
Exactly. Now, their overall volume in the atmosphere is tiny. We measure them in parts per trillion. You might think trillion. That's completely negligible.
But they pack a punch.
They are thousands of times more potent at trapping heat than CO2.
Yeah.
And the worst part is their longevity.
How long do they actually stick around up there?
The text notes that some F gases can persist in the upper atmosphere for 1,000 to 10,000 years.
10,000 years. So if I have a leaky AC unit in my window today, the chemical byproduct of that could literally be warming the planet in the year 12,024.
That is the grim reality of it. We are committing countless future generations, civilizations we can't even fathom yet, to a warmer planet based purely on our cooling needs today. It really highlights the complete failure of that Brundtland contract we talked about earlier.
Compromising the ability of future generations.
Exactly.
Now, normally, nature has a way to handle excess carbon, right? We have natural sinks, trees.
Trees are the absolute heroes here. They are essentially biological containers of carbon. They suck the carbon out of the air and lock it safely into their wood and their roots.
But the reading points out a terrifying inversion happening.
Yes, the feedback loop from hell.
Yeah.
When those forests burn, and we are seeing this happen with increasing severity in Portugal, California, Siberia, Alaska, they switch sides.
They go from being a carbon sink to a carbon source.
Instantly. All that securely stored carbon is violently released back into the atmosphere as smoke and CO2. It accelerates the very warming that dried out the forest and caused the fire in the first place.
So the planet is getting hotter, the greenhouse blanket is getting thicker, but the planet isn't just taking this lying down. The source material talks about planetary adjustments, like the Earth is trying to fix itself, acting like an automatic machine.
It really is. And this is a very complex mechanism. One of the most interesting theories discussed in the source material is the rainfall buffer.
Let's unpack that, because usually we just think of rain as weather. You know, it rains, you grab an umbrella.
But think about the physics we just discussed. A warmer planet causes more evaporation from the oceans. What goes up must eventually come down. So we are seeing a fundamental global increase in precipitation.
Where you might naturally think, more rain falling, that just immediately raises the sea levels, right?
That would be the straightforward logic. Water falls and flows back to the ocean.
But actually the land holds a lot of it.
It does. The scientific evidence shows that extreme precipitation events, like those massive European monsoons, sequester huge amounts of water directly on the landmass. It gets stuck in saturated soils and expanding wetlands and newly formed lakes.
And there's an incredible statistic in the text here. It cites a study showing that land water storage effectively slowed global sea level rise by up to 22% between 2002 and 2014.
It's amazing. So the ground effectively soaked up the ocean like a giant sponge and bought us some time.
It bought us a decade of time.
Okay.
And there's always but in climate science, it comes at a terrible price. This isn't just a gentle, nourishing, misting rain. This is a violent correction.
This planetary adjustment results in what the author calls a dystopia of extremes.
Meaning, we don't just get slightly more rain, we get absolute chaos.
We get a complete paradox. On one hand, you have massive concentrated flooding. Imagine 3 months' worth of rain falling in just a few days. We saw this devastatingly in Germany and in various parts of the U.S.
Yeah.
But simultaneously, often in the exact same year and sometimes in the same region, you face prolonged lethal heat waves.
It's climate whiplash. The weather is constantly giving us whiplash.
And we can actually prove this isn't just anecdotal human memory. We can look at the trees again through dendrochronology.
Tree rings. I loved this part of the reading. It's like reading the diary of the tree.
It's nature's hard drive perfectly preserving the past. You look at a cross-section of a tree trunk. The dense, dark inner rings represent the winter dormancy period. The wider yellowish rings show the summer growth spurt.
And when you analyze these rings over decades,
You see the dramatic shift. You see the stress the tree is under. In places like Aspen, Colorado, the temperature shifts are so violent and so rapid that sensitive tree species are just going extinct. They simply cannot adapt their biology fast enough to survive the whiplash.
and obviously it's not just trees dying. The human cost is right there in the data too. The text mentions the recent heat waves in Europe.
It's a massive tragedy that often happens very quietly. We always see dramatic news footage of floods and hurricanes. We don't often see footage of heat stroke.
No, it happens behind closed doors.
But the text notes that in France, Germany, and Poland, heat waves have become increasingly lethal. In France alone, recent extreme heat waves were linked to 20,000 deaths.
20,000.
And these are mostly vulnerable elderly populations trapped in unair-conditioned buildings. It is a silent mass casualty event directly caused by this planetary adjustment.
And despite this rainfall buffer working overtime, despite the land trying its hardest to soak up the excess water, the water is eventually winning because the ice is melting.
The buffer has a hard limit. It simply cannot keep up with the volume of the glacial melt. The fundamental geography of our planet is literally being redrawn right now. Look up at the Arctic. The melt is so profound that the Northwest Passage is actually opening up.
That's the legendary shipping route, right? The one that explorers died trying to find for centuries.
Exactly. The Franklin expedition famously vanished trying to navigate it. And now, It's becoming a highly viable commercial shipping lane in the summer months.
Which is wild.
It alters global trade, sure, but much more importantly, it signals a catastrophic failure of the Earth's cooling system. And down south at the South Pole, we are seeing a really dangerous imbalance. Ice is growing on one side of the continent while melting rapidly on the other. The whole system is completely destabilized.
And the ocean is taking the absolute brunt of the heat. There was a chart in the presentation that showed exactly where the excess heat goes.
That chart is terrifying to look at. It shows that the vast majority of the excess heat trapped by our greenhouse gases isn't staying in the atmosphere. It is absorbed directly by the ocean. The ocean is acting like a massive heat battery for the planet.
And as water warms up, it physically expands. Combine that thermal expansion with the melting land ice, and this brings us straight to the coastal crisis.
Let's talk about Miami. The projections in the text show Miami is at serious risk of inundation over 91 centimeters.
That is 3 feet of water.
That's not just a wet street during a king tide. That is the fundamental loss of city infrastructure. The U.S. coastline is projected to lose thousands of square kilometers of land.
But a city like Miami has incredible wealth. They can maybe build massive seawalls. They can install giant water pumps. What about Tuvalu? We mentioned them right at the start.
And this brings us back to that core existential question. What happens when a sovereign nation physically disappears beneath the waves? Tuvalu is facing total geographical erasure.
Yeah.
If the land is gone, is it still a country? Do they keep their voting seat at the UN? Where do the displaced citizens go? Who is financially responsible for their relocation?
That's a nightmare.
It creates a legal and moral crisis that our current international laws just aren't built to handle at all.
And this is exactly why the UN established the IPCC back in the day, the Intergovernmental Panel on Climate Change, to get everyone on the same page scientifically.
Right. And for a long time, there was a lot of public debate. Is it human-caused? Is it just a natural cycle? The text actually tracks the evolution of this consensus. In the 1980s, the scientific consensus on human-caused climate change was hovering around 60%.
Basically just a bit more than a coin toss in the scientific community back then.
But today,
Right.
in peer-reviewed published literature, the consensus is over 99%.
Wow.
The debate is completely over. The warming is unequivocal. The question is no longer, is it happening? Or are we the ones doing it? The only question left is, can we stop it in time?
Which brings us nicely to the solution phase of our deep dive. And this is the part that I promised at the beginning would be a surprise twist for you listening.
Yeah.
We have identified the mechanics of the problem. The greenhouse gases, the trapped, the melting ice. Now, who do we actually blame?
We all love to blame aviation. You look up, see a plane leaving a contrail in the sky, and think, there goes the carbon footprint. And yes, obviously flying has an impact. But statistically, the global aviation industry accounts for roughly 1.92% of global emissions.
Just 2%. That's honestly really small. I mean, it's not nothing, but it's certainly not the main villain of the story.
It's a convenient scapegoat. The real giant, the sector responsible for the absolute lion's share of the problem, is the AEC sector, architecture, engineering, and construction.
Hit us with the specific numbers from the report.
Buildings account for a staggering 30% of global energy consumption and 27% of total greenhouse gas emissions.
Wow. So roughly a third of the entire climate problem is just our buildings. The construction of them, the heating, the cooling the concrete.
It makes total sense when you really think about it. A car runs for maybe an hour or two a day. A plane flies for a few hours. A building operates 24/7.
Always on.
It is constantly consuming energy. Plus, it is made of materials like concrete and steel that are incredibly carbon intensive just to manufacture.
There is this really powerful anecdote in the text about the wildfires in Palisades, California. It brilliantly illustrates the power of material choices.
This is such a haunting visual from the lecture. The fire completely swept through the neighborhood. The houses, which were mostly traditional wood frame construction, were utterly incinerated, just gone.
Reduced to ash.
But standing there straight up amidst all the ash and destruction were the brick chimneys.
Just the chimneys left.
Just the chimneys. And why? Because brick has dense thermal mass. It can actually withstand the extreme heat. It is naturally resilient. The lesson the author draws there isn't just about basic fire safety. It's about how our fundamental material choices dictate our survival.
We build cheap and fast.
Exactly. We have been building with materials optimized for speed and cost rather than resilience and energy efficiency.
So if the core of the problem is our buildings, then the vanguard of the solution has to be the architects.
That is what the text calls the architect's mandate. It is very direct about this. If you work in the AEC industry, you are on the absolute front lines of the climate crisis. The new mission is to design buildings that require zero external energy for heating and cooling.
Zero external energy. I mean, that sounds almost impossible.
It's really not, though, especially in places like Portugal where these lecture notes originated. You have the ideal climate, you have abundant sun, you have the technology. We just need to prioritize passive design first.
What does passive design look like in practice?
It means thick, thermally massive walls. It means proper orientation of the building to maximize winter sun and block summer sun. It means designing for natural cross-ventilation.
Let the building do the work naturally.
Right. And then you layer on the active systems, solar, photovoltaics, and thermal energy collectors on the roof.
So the house essentially generates all its own power.
Yes. And the mandate goes way beyond just the individual house. It's about large-scale urban planning, too. We urgently need to reduce the urban heat island effect.
Because cities are always hotter than the surrounding countryside.
Exactly, due to all the dark asphalt and concrete absorbing heat. The solution proposed: plant forests right inside the city. Use extensive vegetation to cool the streets down naturally through shade and transpiration.
It sounds like we need to radically rethink how we build entirely. But is it enough? I mean, can better buildings really save the planet on their own?
Not entirely on their own, no. And that leads us to the wedges strategy mentioned in the sources. There's a really helpful visual called the stabilization triangle.
I saw that in the PDF. It looks like a big steep ramp of carbon emissions going up.
Yeah.
You need to flatten the top of it.
Exactly right. And the core idea of the triangle is that there is no silver bullet. There isn't just one magic future technology that fixes everything at once.
Right.
We need multiple wedges. Each wedge represents a totally different strategy that cuts 1 billion tons of carbon emissions over time.
So, for example, one wedge might be transitioning to efficient electric vehicles. Another wedge could be aggressively stopping global deforestation.
Another wedge is scaling up CO2 capture technologies. But a massive, absolutely crucial wedge in that triangle is improving building efficiency. If we ignore the AEC sector, we simply cannot solve the puzzle. We mathematically cannot flatten that curve.
It's actually quite empowering in a way. It means that the ultimate solution isn't just locked away in the hands of some high-level diplomat in Geneva.
No, it's very local.
It's in the hands of the contractor pouring the concrete. It's in the hands of the architect drawing up the blueprints.
And crucially, it's in the hands of the client, too. The person buying the house, the person renting the apartment or leasing the office space.
So let's zoom out a bit here as we wrap up. We have covered a tremendous amount of ground today. We have gone all the way from the illusion of escaping to Mars down to the burning forests of California and the resilient brick chimneys of the Palisades.
It is a giant interconnected puzzle. The source material actually uses that exact puzzle imagery at the end. We finally know what all the pieces are. We understand the natural solar activity. We've measured the trace gases. We see the ocean heat capacity and the sheer scale of human consumption.
The fundamental science is completely settled. We know the what and we know the why.
But the how is the hard part.
And the how is now completely up to the professionals. And this is the final provocation I want to leave with you listening today. The source material we used was originally a lecture designed for university students, future architects, and engineers.
But the core message applies to absolutely everyone.
Because we all live in buildings. We all use energy every day.
Exactly. If the building sector is the massive hidden problem, it is also our most vital, accessible solution. Every single time you choose a building material, every time you design a window placement, every time you decide where to live or how to renovate a space, you are casting a direct vote for the climate.
You are voting for the kind of future you want to inhabit. And thinking about that, if every building choice is a climate vote, what if we push that even further?
How so?
Well, the mandate says zero emissions, right? But what if the future of architecture isn't just neutral? What if buildings could become the new trees?
Like active carbon sinks.
Exactly. Imagine a city that doesn't just produce zero carbon, but actually pulls carbon out of the atmosphere just by existing.
Yeah.
That's the next frontier we should be aiming for.
That is a brilliant way to look at it. The clock is ticking. We all saw that stark image of the 11th hour. But the beauty of a clock is that the hands do keep moving. We still have the agency to choose exactly how the next hour plays out.
That is the big takeaway here. Ban Ki-moon was entirely right. There is no planet B. So we have to roll up our sleeves and fix planet A.
It's the only home we have. Let's get to work.
Thanks for joining us for this deep dive. It's a really heavy topic, I know, but hopefully you feel a little more armed with the actual facts and the mechanics now. Catch you on the next one.